Okay, so let's imagine now that we have two objects, and one is at a height h, and we launch it straight down at some unknown speed. Let's call it v naught y, because there's a vertical speed, and it's going to hit the bottom at some speed, and then there's another object that is dropped from half that height, so h over 2, and they both reach at the same time. So they hit ground at same time, and we want to find the speeds or the component of the velocity, which these are vertical components. But either way, okay. So let's look at the ball or object that is dropped and see what the equations look like for that. So it's dropped from a height h over 2. So the natural thing to start with is the Vy equation, right? So the v naught y in this case is 0, so we simply have minus g times t. And so we need the time, and that forces us, of course, to the other kinematic equation. So y, which is 0, we want the time when it reaches y equals 0, right? Because this is y equals 0. It starts at h over 2. There's no initial vertical component, so the other part of this is 1/2 gt squared, and that's what the y kinematic equation looks like for the ball or object that is dropped. And so, of course, we can get the time where we'll bring this to this side, and we'll multiply by 2. We'll divide by g and take the square root. So we get h over g square root. And then we can plug it back into here and get the Vy, which is minus g, times that t, which is h over g square root, which is minus the square root of g times h. And so if we want the speed, it's just the square root of g times h. But that's the vertical component, which obviously is negative, for the ball that's launched straight down at some unknown speed. What do the equations look like? Well, we want the speed at the bottom, so we want the Vy, just like we do here, but that looks a little different now. We have the minus v naught y minus gt, because there's the initial component. But we know the time, so we know it's going to hit at the same time. So this becomes minus v naught y minus g times square root of h over g, which looks like minus v naught y minus gh square root. And so we need v naught y to find the Vy with which it hits the ground. So that forces, of course, to the other kinematic equation. So it's going to hit the ground when y is 0. It starts at h in this case, because we're up here. We have a component, an initial component, which appears there as well, of course. Here it appears with t, because it's the integral of that to get the position, minus 1/2 gt squared. But we already know the time, right? So we can use this equation to find the v naught y and then plug it into there to find the Vy. So from this equation, v naught y is equal to what, right? We'll take this term and bring it over here so that it's positive, and then we have to divide by t, and so we'll get h over t minus 1/2 gt, because we divide that term by t as well, and now we can replace the t with the known value. So this becomes h over g minus g over 2 h over g square root, which is hg square root minus 1/2 hg square root, which is 1/2 hg square root. So we have the v naught y, we plug it into there, and we get our vy, which is minus hg square root over 2 minus the square root of hg, which is minus 3/2 square root of hg. So we're comparing these two things. The speed of the object that was launched downwards from a higher height is 3/2 the speed of the other object.